Welcome to UGC lecture series, BSc Physics Honors, Semester 6, Statistical Physics, Lecture 14. In this lecture, we are going to see some of the applications of Fermi-Dirac statistics. We have learnt many statistics under the category of classical statistics and quantum statistics. A statistical mechanics which is explained based on classical mechanics is called classical statistics. Example of classical statistics is Maxwell-Boltzmann statistics. Then example of quantum statistics is Bose-Einstein statistics and Fermi-Dirac statistics. In Maxwell-Boltzmann statistics, the velocity distribution of particles or velocity distribution among the particles is obtained, and the number of particles in each energy level is learnt. Then the energy value of each energy level is also derived. This classical Maxwell-Boltzmann statistics is an important tool in statistical mechanics. It couldn't explain some of the properties like specific heat capacity, photoelectric effect in application area. Then Bose-Einstein statistics came. In Bose-Einstein statistics, Einstein used the Planck's hypothesis, which is nothing but energy are in the form of wave. Black body radiations are in wave form. Black body radiation energy value is E is equal to h nu, where nu is the frequency. All these things are proposed by Planck, Maxwell Planck in the year 1900. Einstein used this concept and along with Indian scientist Bose, he proposed that Bose-Einstein statistics. But this Bose-Einstein statistics couldn't explain very well about the specific heat capacity of the material. Electrical conductivity of the material is explained, then thermal conductivity is explained, but specific heat capacity is not explained by Bose-Einstein statistics. Materials or particles which obey this Fermi-Dirac statistics are called as fermions. This is how the history of statistical mechanics can be learnt. Now, application of these statistical mechanics. The main and major application of the statistical mechanics is the white dwarfs. This is a kind of star which is in the celestial area, which is a celestial object. This white dwarf is a kind of star in the universe. Many other stars are there, but here the Fermi-Dirac statistics is applied to this white dwarf. In this lecture, we are going to derive the expression for energy of this white dwarf, Fermi energy of this white dwarf. In that Fermi energy, mass quantity is there. By applying some limit to that mass, Chandrasekhar limit comes. That is what we are going to do in this lecture. Now, white dwarfs are stars which are very much fainter than other stars. Then this possesses smaller diameter and very dense as compared to the other star at the same mass. We have many stars in this universe. Our sun is also a star. That sun gives energy to our earth, heat energy and light energy. Main source of heat energy in sun is hydrogen. Fusion of hydrogen into helium produces this energy. Nuclear fusion is the main physics behind the production of energy in sun. Like that, all stars also produces energy, light energy as well as heat energy. These stars are far away from earth. That is why it appears very tiny in the night sky, but Sun is a big star in our universe. Here these white dwarfs are also stars which are fainter than a smaller star. Then this possesses smaller diameter and very dense as compared to the other stars of system. Content of these white dwarfs will be helium. You know, it is a chemical compound which is formed by the fusion of two hydrogen atoms. Mass of these white dwarfs are 10 power 30 kilogram, approximately 10 power 30 kilogram, which is approximately equal to the mass of the Sun. Then density of white dwarf is 10 power 10 kilogram per meter cube, which is 10 times denser than Sun, 10 power 10 kilogram per meter cube, which is 10 times greater than the density of the Sun. So, at high temperature this helium gas gets completely ionized. Such high temperature of these white dwarfs are 10 power it will be equal to the temperature of the Sun. Inner core of the Sun will be, inner core temperature of the Sun will be some billion degrees Celsius, that is 10 power 9 degrees Celsius, 4.5 billion degrees Celsius is the inner core temperature of the Sun. So, white dwarf also has such high temperature. At this high temperature, the helium gas inside that white dwarf gets completely ionized. You know the process of ionization, splitting of a neutral atom into positive ion and negative ion. This could happen in high temperature because temperature supplies energy. When heat energy is supplied, temperature will rise. This supplied heat energy will split or will collapse the neutral atom. So, electron from an atom can attach to the electron to the other atom. So, the detached, an atom in which electron is detached will become positive ion. That detached electron will go and attach, get attached with another neutral atom. So, that neutral atom will become a negative ion. This is how positive ions and negative ions are produced. The process of production of positive ions and negative ions is called as ionization. At such high temperatures, that is 4.5 billion degrees Celsius, this helium gas inside the white dwarfs gets ionized. So, that white dwarfs may be considered as a complete gas composed of helium nuclei and electrons. In such high temperature Fermi energy, we know the mathematical expression for Fermi energy at 0 Kelvin, that depends on volume of the system and density, mass, Planck's constant. All these factors decides the Fermi energy, mass of a Fermi energy of the system. We know the mathematical expression to calculate that. Just use that same mathematical expression here to get the Fermi energy level. So, Fermi energy E suffix F is equal to h square by 2m into 3n by 8 pi v to the power 2 by 3, which is approximately equal to 20 million electron volt. This is the Fermi energy level of the helium nuclei. So, here total number of atoms in the system, then volume of the system, mass of the system. So, you got this Fermi energy level. Then Fermi temperature, that Fermi temperature is denoted as T suffix F. That Fermi temperature is approximately equal to Fermi energy over Boltzmann constant. That Fermi energy is 20 million electron volt. Convert the 20 million electron volt into joule. So, you will get 1.6 into 10 power minus 13 over Boltzmann constant 1.38 into 10 power minus 23 which will be approximately equal to 10 power 11 Kelvin. As I told, billion Kelvin is the core temperature of the sun. Here you got 100 billion Kelvin, that is the Fermi temperature of the helium gas or white dwarf, because at high temperature that white dwarfs will be a complete gas cloud. Temperature of that one will be 10 power 11 Kelvin. Here, as the ratio between the Fermi temperature and the temperature is very greater than 1, the electron gas which is assumed is highly degenerate. The electron gas is highly degenerate. So, we can regard it as a Fermi gas at T is equal to 0 Kelvin. We can regard this as a Fermi gas at T is equal to 0 Kelvin. You know, the expression for Fermi gas at absolute 0 Kelvin, in last lecture we derived that. That expression can be brought here and you can get the Fermi energy at 0 Kelvin, because the white dwarfs can be considered as a Fermi gas. The single particle energy level can be given as epsilon Ps. Single particle energy level can be given as epsilon Ps is equal to P square into C square plus m square to the C power 4 the whole power half, that is square root of P square C square plus m square C power 4. This is the single particle energy level, where P is the momentum and m is the rest mass of the electron and C is the speed of light. You know the value of speed of light. The value of speed of light is 3 into 10 power 8 meter per second. Then the electrons at as stated between the momentum P and P plus dP, total number of particles between the momentum P and d plus dP having spin s. So, the ground state energy of Fermi gas is given as E suffix 0 is equal to Gs, which is a spin degeneracy factor, into epsilon summation over P, magnitude of P which is lesser than Pf, into P square C square plus m square C power 4 to the power half, square root of P square C square plus m square C power 4. So, this will give the ground state energy of the Fermi gas. Here that white draft is assumed as a Fermi gas. Ground state energy of that Fermi gas is given like this. Now, Pf is the Fermi momentum. This P suffix f is the Fermi momentum. This Fermi momentum is given by P suffix f is equal to square root of 2 m epsilon f Fermi energy, which is equal to square root of 2 m into h square by 2 m into 3 n by 8 pi v to the power 2 by 3, that is square of the cubic root. This is the Fermi momentum. Further simplification of the above expression gives the Fermi momentum as Pf is equal to h into 3 n by 8 pi v to the power 1 by 3. This is the mathematical expression for Fermi momentum. Now, As the energy levels are quite closer to each other, the summation may be replaced by integration to get the energy level. So, the expression will be replaced as Gs, G suffix s, which is a spin degeneracy factor, is equal to G of P dP is equal to 2s plus 1 into V into 4 pi p square dP by h cube. This is the mathematical expression to calculate the spin degeneracy factor. Now, this can be further reduced for electron as for electron the spin s is equal to 1 by 2. So, G s will get a value as 2 into V into 4 pi p square dP by h cube. So, this is the spin degeneracy factor for electron, because s is equal to half, spin of an electron is half, that is substituted here, we got this expression. Now, the ground state energy will become E naught is equal to 2 V by h cube integral of 0 to P f. Here the integration is replaced by summation. The reason for the replacement of summation by integration is the energy levels are very closer, so that summation can be replaced by integration. So, integration between 0 to P f of p square c square plus m square c power 4 to the power 1 by 2, that is square root of p square c square plus m square c power 4 pi p square dP. This is how this is the expression we will get for the ground state energy or Fermi energy or ground state energy of a Fermi gas. Now, substitute P by mc is equal to x in the above expression. So, this can be simplified further to get the value of dP by mc as dx. Substitute this thing in that ground state energy level expression. So, the ground state energy expression E naught is equal to 8 pi V by h cube into integration between 0 to x suffix f, which is nothing but P by mc into m c square into 1 plus x square to the power 1 by 2, that is square root of 1 plus x square into m c x the whole square m c dx. This is how the ground state energy value expression will change after substituting P by mc is equal to x and dP by mc is equal to dx. Further simplification of the above expression gives 8 pi V m power 4 c power 5 over h cube integration between 0 to x f of 1 plus x square to the power 1 by 2, that is square root of 1 plus x square into x square dx. Further simplification of this equation gives E naught, that is ground state energy E naught is equal to 8 pi V m square c power 5 over h cube into f of xf, f of xf. Here this f of x can be evaluated as f of x is equal to f of xf is equal to integration between 0 to x f x square into 1 plus x square power 1 by 2, that is square root of 1 plus x square into dx. This can be classified as f of x f is equal to two values are there, 1 by 2 x cube x f cube into 1 plus 3 by 10 into x square x f square plus etc. This is one kind of value for the x f lesser than or equal to 1. For x f greater than or equal to for x f very greater than 1, this f of x f will give a value as 1 by 4 into x f power 4, fourth power of x f into 1 plus x f minus 2, 1 plus x f minus 2 plus etc. This is how the f of x f value will become for different values of x f. Now, let us take the condition x f very lesser than 1. This corresponds to non-relativistic case and this x f very greater than 1 correspond to relativistic case. Non-relativistic case and this corresponds to relativistic. Now, let us go for the pressure. Pressure can be obtained by x f is equal to P f by m c. So, pressure P naught can be obtained is equal to minus dou E naught by dou V. So, pressure is nothing but partial differentiation of ground state energy with respect to volume. So, partial differentiation of ground state energy with respect to volume gives minus 8 pi m power 4 c power 5 by h cube into f of x f plus V into dou f of x f over dou x f into dou x f by dou V. This is how the expression will become for pressure. So, to get pressure we have to partially differentiate the ground state energy with respect to volume. Now, which is equal to 8 pi m power 4 c power 5 by h cube into 1 by 3 into x cube f into 1 plus x square f to the power 1 by 2 minus f of x f, This is how that pressure expression will change. This pressure expression will further split into two types, that is 8 pi m power 4 c power 5 by 15 h cube into x f power 5 for x f very lesser than 1. For x f very greater than 1, that pressure will become 2 pi m power 4 c power 5 by 3 h cube into x f power 4 minus x f square. So, this is how the pressure will split into two types for two different conditions. Now, if m is the mass of the electron, and mp is the mass of the proton, and n is the number of helium atoms, then mass of star can be computed. Here we are discussing about white dwarfs. Here we are applying the Fermi-Dirac statistics to this white dwarf, that is energy of the white dwarf. Now, what we have obtained so far is so far we have got the pressure inside the gas and temperature of the gas, gas in the sense that white dwarf is assumed as a gas. So, it will behave as a gas, because at high temperatures it will be ionized. So, it will behave as a gas. The temperature of the gas will be 10 power approximately 10 power 11 Kelvin, which is nearly equal to 100 billion Kelvin, 100 billion Kelvin. Now, we are going to get the mass of the star. So, mass of the star m is equal to m plus 2 mp into n, where this m is the mass of the electron, mp is the mass of the proton, n is the number of helium atoms, which is equal to 2 mp n, because this m will be very lesser than mp. Mass of the electron will be very lesser than mass of the proton. So, we got this as the mass of the star. Now, radius of the star V is equal to 4 by 3. To get the radius of the star, we have to go to the volume of the star, that is 4 by 3 pi r cube is equal to, from this r value is equal to 3 V by 4 pi to the power 1 by 3 to the power 1 by 3. So, you will get the radius as this one. So, finally, the gravitational constant of the gas is substituted, of the star is substituted. So, at equilibrium condition, the pressure P naught is equal to 3 by 20 pi into g m square by r power 4 after substituting all the gravitational constant. So, this is the equilibrium pressure in terms of mass of the star and radius of the star. So, for extreme relativistic case, this xf will be very greater than 1. So, no white dwarf have a mass larger than m naught is equal to 8 by 9 pi into mp into 45 by 64 pi to the power 3 by 2 into hc by 2 pi g mp square to the power 3 by 2. This is the limiting mass of the gas. This limit is called as Chandrasekhar limit. Value of this Chandrasekhar limit will be approximately 10 power 30 kilogram. This is how statistical mechanics can be applied to get the limiting mass of the star, white dwarf stars. Here pressure is calculated and all other things are mathematically substituted. The final limiting mass will be 10 power 30 kilogram. This white dwarf cannot have mass more than this 10 power 30 kilogram. This is proposed by the Indian scientist Chandrasekhar. So, the name Chandrasekhar limit is given to this statistical mechanics concept. So, in this lecture we have discussed and derived things about white dwarfs, application of statistical mechanics, especially Fermi-Dirac statistics to white dwarfs. These white dwarfs are stars which are much fainter. Fermi-Dirac statistics can be applied to these white dwarfs. From the derivation of the white dwarfs, we will get the Chandrasekhar mass limit, which is approximately 10 power 30 kilogram. That means a star cannot have more than 10 power 30 kilogram. So, that is the Chandrasekhar limit. After listening to this lecture, you can answer the following questions. what is known as white draft, define Chandrasekhar limit, define specific heat capacity using Fermi-Dirac statistics. Thank you.